okay now. And so the focus in this presentation is on the energy management agent component. I will first give you a short introduction, then present the main methods and approach applied in the project. We had several case studies. Unfortunately, I have only 20 minutes, so I will just present some details with one of the case studies to give you an overall idea of the work and advances done in the project. And then we also have, as part of the work, made several publications on the AI-based modeling optimization. So if you are interested on the details, I will also present or quickly show the publications we have published as part of the work. Okay, so of course, in the smart neighborhood and in these districts, we can have different type of energy resources. Joseph just showed you the battery and EV charging. The work in this with the energy management agent has mainly focused on buildings, which are also important for energy management and demand response, because buildings are major consumers of energy, and buildings also have a natural storage of energy because they typically have a large thermal mass that can be used to shift heating either provided by electricity or district heating into different time period. And of course, the aim in this work has been to create accurate models on the heating, on the HVAC systems, and kind of enable the flexibility of the buildings to be used both for implicit and explicit demand response at the same time. However, there are challenges. The HVAC systems and heating is quite complex, and there's non-linear dynamics with very long feedback cycles caused by the thermal mass of the building. Also, it's important to avoid, not just to optimize the building with respect to some external prices, because we want to avoid local optima. So it's important at the same time to kind of open the flexibility and offer it for the local market, and through the local markets also for the aggregator, so that it can be used for the situation that is the most important, as long as the consumers and prosumers are properly compensated. Okay, this slide shows the overview of the approach we studied in the project. So here is the energy management agent that tries to model and optimize the flexibility and energy of an energy system, and here the focus was mainly on buildings. And the approach we applied was that we used machine learning, mainly artificial neural networks, in combination in some of the case studies, in combination with physics-based modeling, to create accurate models of the energy system. And these models together form like a digital twin of the energy system of the building that can be then used for model-based optimization and planning in order to find the best way to control the building heating, for example. So this is somewhat, so here we use somewhat similar approaches that have been used in, for example, this game playing AI algorithms by DeepMind, this AlphaGo and AlphaZero. But in order to be able to do that, we first need to create the models that can be used to optimize in the digital world through simulation. Okay, here is the kind of internal architecture. So how is the energy management agent divided into different parts? As already shown earlier, the energy management agent operates between the trading agent that tries to maximize the value in the markets and the IoT middleware that Erkin and Joseph were presenting in the earlier presentation. The energy management agent consists roughly on three types of components. So we have the digital twin, the models here. We have the energy planner, which is like a supervisory controller within a building or within a consumption site. And the energy planner, its job is to optimize the load, for example, the heating load for the site. And this is done, for example, with respect to dynamic electricity prices. It also, and when it has optimized the plan, it informs the trading agent about the load plan it's planning to follow in the next market window. It also evaluates the flexibility, which is basically the possible deviations from the load plan. And this information is also provided to the trading agent. And when the trading agent is trading in the local markets, it can inform the energy planner about the changes, about the trades via the change to load plan message. And the energy planner uses these models to kind of simulate and optimize or plan the load through simulation, let's say. Then there's also a controller component. There's one controller for each flexible asset in the system. So for example, one for the heating. And once the energy planner makes the plan for the whole site, it also makes the load plan for every controller. And the kind of role of the controller, the job of the controller is to try to track or follow the load plan. And it can also use the models to do model predictive control in similar way as the energy planner is doing. And then finally, the control commands are executed through the IoT middleware. We implemented and studied 4 different sites, 4 different case studies in the context of the energy management agent. We did modeling and optimization for apartment heating. This was done in our test apartment in the Oulu. Then we did electricity and heat demand forecasting for an office building located in southern part of Finland in Espoo. And we investigated new type of neural network architectures here. Then we also had the possibility to work with the supermarket. So we did modeling for the heating dynamics on the supermarket, as well as implemented forecasting models for forecasting the flexibility and electricity loads at TUM's smart office. I don't have now time to go through all these case studies, but just to give you an example, I will focus on the first case study a bit more in detail. So here is a visualization of the case study. So it was implemented in our test apartment, which is roughly 70 square meter apartment. There are quite advanced metering infrastructure. We get the energy measurement from various submeters at 1 minute resolution. There is the heat pump, which was the main flexible asset in this case study. There's also various sensors for temperature, CO2, humidity, and so on that can be accessed by the by the energy management agent. So the energy management agent is here. It consists of the models and then the optimization and control. For modeling, we used artificial neural networks. I will show more details in the upcoming slides. And then for optimization and control, we studied Monte Carlo tree search, which is also the core algorithm behind this AlphaZero and AlphaGo. Here is a simple illustration on how does the information provided to the trading agent look like. So here are the up flexibilities, down flexibilities. It's now actually in this this time. So this is actual measured energy, and here are some activated down flexibilities and activated up flexibilities. Okay. So basically, the energy management agent consists of modeling, the flexible resources, and then the optimization part. So for the modeling, we implemented two models, two neural networks, one for the modeling the heating, so the energy consumption of the heat pump, and one to model the indoor temperature of the apartment. And for modeling, we use 15-minute resolution. For training and kind of finding the hyperparameters for the models, we used this period, 43 days, and then we evaluated and tested the models in this period, which consisted of 29 days. We use standard root mean square error and its normalized version as error metrics. Here is the temperature model or visualization of the temperature model. We achieved quite nice results, around 3% error in 1 hour, so 4-step forecast. Here you can see the autocorrelation. So how do the errors of the model correlate? And you can see there is basically no correlation. This looks pretty much like a white noise. So it means that there's not much signal left in the errors. So the modeling, at least let's say linear correlation in the errors. So the modeling has done quite good job, and also the accuracy is good. Here is the energy consumption model. It's a bit more complex, so it consists actually on 2 parts. The second part was added just to correct, because there was still quite strong signal left in the error after the first model. So we added that just to try to fix the forecast based on the residual information from past errors. We achieved around 8% error for the energy consumption modeling. Also, this was done for one hour window. Here you can see that there's a bit stronger correlation, but still it's very minor, and it was not. We couldn't find a way to improve the results. So this is also good results. Then these models were used, like I said, in planning and control. So both the energy planner and the controller use these models to plan how the heat pump should be used, but then also to control the heat pump. And the heat pump was controlled by adjusting the set points, temperature set points of the heat pump, and these were the allowed values. I will not go into detail how this Monte Carlo tree search works, but the basic idea is that it kind of form a graph by forecasting different or taking different actions. So these set points at different time periods, and you can imagine that it kind of forms a big graph. And then instead of going through all possible scenarios, which is not possible because for example, if we optimize in 24-hour window, there's quite many different scenarios. So the Monte Carlo tree search is a kind of, in a way, machine learning algorithm, or it learns and tries to search parts of the tree that seem to be more optimal. So it kind of targets the search to those policies, those policies that seem to return better value. Okay. Then how did we evaluate the approach? So we wanted basically to know two things: how much this energy management agent is able to reduce costs when compared to a baseline control strategy. So the baseline was just keeping the temperature at fixed value, and this was done and the optimization was done with respect to Nord Pool spot prices. So here you can see the spot prices for the evaluation period. Here is the price in euros per megawatt hour, and here is the outdoor temperatures in Oulu or in the site during the evaluation period. Then, like I mentioned earlier, we also didn't want to just focus on local optimization, but also wanted to offer the flexibility for the local market and through the local market also to the aggregators. So in this context, it's important that the energy management agent or the behavior of the building is predictable. So the load plans need to be accurate. The response of the energy management agent when it's controlled needs to be accurate. So this was another thing we wanted to evaluate. The evaluation period was 16 weeks between this period, and it was done by simulating with the models I showed earlier, but then sampling errors from the empirical error distribution I showed earlier, not to give the optimization kind of unfair benefit. Okay, so in the first scenario, we just did the spot price optimization. On the top part of the figure, you can see the daily energy costs here, and here the cumulative energy costs compared with on blue is the fixed set point controller, so the one that keeps the temperature at fixed value, and then the energy management agent that was allowed to increase the temperature or drop it half a degree below the 23 Celsius degree. In this evaluation, we only measured the spot price, the energy costs, so this didn't include any taxes or network fee, which typically constitute like a 2/3 of the price. But anyway, the energy management agent was able to achieve a bit below 15% lower costs when compared to the fixed set point controller. Here on the bottom part of the slide, you can see a couple of examples. So the orange line is the energy price, and the blue line is the energy consumption of the heat pump, and this data is in 15-minute resolution. So you can see that the heat pump kind of exploited or learned to exploit the low price periods. It also used quite short bursts of heating to keep the temperature just above the minimum value. Okay, here is another scenario. Here the energy management agent, like I said, is all the time offering the flexibility for the trading agent. And here we want to evaluate how accurate those load plans are and how predictable, how well we have done the modeling, and how well we can, with the control kind of even improve the accuracy of the models, because we can try to kind of, in a way, fulfill the prediction. So what you can see here is that on blue, you have, this is 1 hour resolution, so that's why the data looks a bit different to the previous slide. It's more low resolution data. On the blue, you can see the original load plan that was done for the day. Then for every day during the evaluation period, we selected the hour with the lowest price and then execute the flexibility or demand response event there. the idea was that all the sites would be kind of exploiting the spot prices, and then there would be like a local bottleneck in the network. And here you can see the flexibility that was kind of estimated, so between the blue and red one, and then the green one is the actual measured load. So you can see that typically there's some errors, but typically it's able to quite accurately follow the estimates. And outside of the flexibility events or demand response events, the errors were roughly 5%, and then during the events it was a bit above 7%. So still very accurate results. So just to summarize, we were able to reduce the costs while at the same time offer the flexibility for the local markets, and this was kind of the goal to be able to provide both implicit and explicit demand response at the same time. And if you are interested, here are some of the publications we have done on this case study, and then we have some others for the other case studies. But thanks, this was my presentation, and I think now we move to the was it trading agent